Okay, so I've added the finite state machine to our little mini LED game. And basically it's right here on this breadboard. So all these chips here, these are kind of and OR gates and with a not gate chip. And this longer chip at the end here, this is the 74HCT273, not 283, my bad. And this is our D flip-flops. And so from our finite state machine, you see we have all these jumpers over here that are going out to control the various control signals for our LEDs and the counter. And we also have the clock running through it, and our push button is attached as well for our input. And so now all we got to do is add power to the circuit and see if it works. Okay, reset, and we push the clock in. Maybe speed it up a little bit. And it's working on the green. We're in that first state. Okay, it moves on to the red and the blue. And it comes to a pause, and nothing else should happen until I hit the reset button. Let's turn off the clock. Okay, so it looks like it works. Now we should kind of go through it a little more slowly. Make sure we don't see anything funny. Yeah. Seems to be working okay. Aha. We have ourselves a little bug. And I am not too surprised because I had this exact same bug on the first build of this circuit. And to be honest, I never really bothered to fix it. So let's go see what the bug is. If our clock is moving along, we hit the push button. On the next clock cycle, it goes to the first LED of the next state. Now, if I push the push button on that very first LED, then when I hit the clock, it should jump to the blue, yet it does not. But if I hit the push button again, then it does go to the blue LED. So on that first LED, it kind of gets stuck there. And when I first ran into this, I didn't bother fixing it, because really, when you're playing the game, if you're to play this game at kind of any moderate pace, this is not even fast, like, that's normally how you would play the game. And since it's going so fast, you would never really be able to hit it on that first LED. It's just, you can't be faster than the clock. If your hand is faster than the clock, the game is too slow and it'd be boring. And so I didn't bother to fix it. But if I'm going to put an internet video out here, I can't be so lazy. And so let's see what on earth is the problem, because it looks like it's something either with our finite state machine or probably the push button. And let's turn off the power and start debugging, shall we? Okay. All right, let's see what is happening here. If we go check our little push button over here, it's low as it should be. And if it moves along, now if we activate the push button, it should jump up high as it does. And then we hit the clock, it goes down low and resets itself. Hit the push button once more, it should go high. And it doesn't. So there's our problem. We hit the clock, hit the push button, and it goes high. So on that second consecutive push, it is not going up. So if we push now, it should go up, but it stays low. Yes, it does. And so there's our bug. That's the problem we got. And so now we got to go to the schematic and see what on earth we did wrong. All right. So we have a bug in our LED game which does not allow us to hit the push button on 2 consecutive LEDs. And we know that this is coming from some error in the synchronized pulse circuit. And so let's go through its operation and see if we could figure out what is going on here. So here's how it starts off. D1 is always high, and Q1 and Q2 are low. And of course, since Q2 is low, Q0 has to be high, and so the reset of the first D flip-flop is not activated. And I have some like 3 LEDs drawn up here with the first one lit. And so if the player hits the push button when the first one is lit, well, Q1 goes high and the Q2 not stays high, and so there's no reset. But on the very next clock pulse, the input from the D2 forces Q2 high, and so Q2 not goes low and resets the first D flip-flop. And at the same time, the second LED is lit up because we're on the next period of the clock. And so we come over here, Q1 is reset, we're on the second LED, but we know that if we hit the push button, nothing happens. We have to wait for the next clock cycle and the third LED for us to be able to hit the push button and have something happen. And we could see why this is because while the second LED is lit up, Q2 naught is low, and so the reset is activated. And so if this reset is activated, well, that overrides anything that happens on this Q1 here. So even if we hit the push button and try to bring the input high, well, it's going to ignore it because the reset is forcing that guy low. And so this is our issue. This is our problem with our circuit. Now, to solve this is that we have to disactivate this reset. But we can't completely deactivate it because that's kind of part of the whole operation of our circuit. We need to be able to reset our D flip-flop on that first strike of the clock, but we need to quickly bring it back high, before the next strike. We don't have time to wait around for the second clock pulse. It has to be very fast. So we just want to reset this D flip-flop and then immediately bring the reset back high so it could be ready for another push of the button. So since the reset of let's look over here. Since the reset of this first D flip-flop is controlled by this second flip-flop, what we can do is reset this second flip-flop. So once this guy goes high and he goes low, we could kind of, if we tie say a wire here, we'll reset this second D flip-flop, and he'll go back high and no longer be forcing the output of Q1 to low. But we have to be a little careful here, because if we simply tie a piece of wire straight to the reset, well, the moment Q2 goes high, Q2 naught's going to go low and it's going to reset himself. And so he's just going to go up for a brief second and come back down. In fact, a brief second, some tens of nanoseconds. It's going to be a tiny amount of time. And it's going to be such a short amount of time that it might not be long enough for the first D flip-flop to be reset, because the distance from here to here is going to be much shorter than the distance from here to here. And so what we want to do is reset the first flip-flop, and then a short time later reset the second one. And we could do this by using a low-pass filter. So if I just draw ourselves a little RC filter here, something like this should do the trick. This way, when Q2 goes low, it's just gonna be a straight wire going right to R1. We'll reset the first flip-flop, but there's gonna be some delay on the reset of the second one because of this low pass filter. Now, we want it to be fairly quick. In fact, we want this delay to be just long enough so that the first flip-flop can be reset. So we could put something like a 10 kilo ohm resistor and a 100 picofarad capacitor. And so if we look kind of at R1, he's gonna come down fast like this. But if we look at R2, he's gonna have that slow kind of curvy down. And so the difference between a fast drop and this slow one should be enough to allow us to reset the first one, then reset the second one. And once the second D flip-flop is reset, well, our push button will be activated and we'll be able to hit it on that second LED. Okay, so now we just have to plug it in the breadboard and see if this little low pass filter trick works out. Okay, so I have added the 10 kilo ohm and 100 puff cap on the reset of the second D flip-flop, whereas this orange jumper wire here goes straight to the reset of the first one. And so let's power on our circuit and see what we get. Okay. Hold on a second. So there's our clock going along, and here's our player's pulse, of course. But we want to check out the resets. And first, we could do it. Yeah, let's check out the resets. And so the white trace, or the very baby blue trace, that is our R1 reset. And you see when the clock strikes, the white immediately drops down and resets himself. Whereas the R2 reset is delayed, right? It's slower. You see it takes some time to come down. And basically once he crosses that threshold, well, the R1 jumps back up high. And at the same time, R2, of course, it comes back up high as well. And so that's what we want. We want it to reset enough so that our pulse goes down, but we want it to come back up very quickly so that we're ready again for another push of the button. And so there's about 1 microsecond per division, so it's extremely fast. And if we go to the long view here, maybe a little longer. Actually, I should increase the frequency perhaps. There we go. And now we can see we could get 2 pulses and 2 clicks of the button within 1 cycle. So the first LED will be lit on this cycle, we hit it, and then the next LED will be lit on this one, and we could hit it, right? Before we had to wait till after this second pulse of the clock, and then we were able to use our push button. So just by adjusting our resets so that it resets very quickly, we kind of solved our bug. And there's a second slight issue as well, and this has to do with our finite state machine and how it operates. When our clock at the top here strikes, we want to ensure that the pulse is still high. Our player's pulse is still high. So you can see the player's pulse kind of drops immediately once the clock is struck high, and there's like almost no margin, I don't know, what's that, 10 nanoseconds of margin. So there's almost 0 margin. And if we want to just be a little safe and ensure that when the clock does strike, our player's pulse indeed has a solid high, we could rearrange the circuit in a way. Let me just turn off the power. And what we can do is, instead of using a wire to connect to the reset of the first flip-flop, we could use a 10 kilo ohm resistor. Let's just stick it in right here. And if we power this circuit on again, hit our push button, we see the change in the response. If we look at the white curve here, he's no longer dropping down immediately. There is a slight bit of delay, but it's still much quicker than our green fellow over here, which is the R2 reset. And that's because we haven't added any capacitor. We just put in a straight resistor. Yet if we look at it, it looks like an RC time constant, you know, and in fact it is. And the capacitor for this RC time constant is just the parasitic capacitance of our circuit over here. You know, there's always this junk capacitance just floating around inside the breadboard, all these wires up in here. And so that, in combination with our resistor we put in here, causes this sort of delay. And because of this delay, we see that our player's pulse, you know, kind of stays a solid high right throughout that full clock strike there. So therefore the clock, on that upper edge of the clock, we know for sure the player's pulse is a strong high. And so we got some 500 nanoseconds kind of a margin there, which is more than enough. We just want to make sure that there's no he doesn't kind of get tricked and fall too quickly for our finite state machine to make a false reading. Okay, so this kind of solves two of our problems. One, it gets rid of the bug because we're just resetting our chip immediately after. And two, we kind of ensure that the finite state machine does read a good high on the player's pulse, you know, while the clock strikes. There's one more issue with these D flip-flops that we got to check out, and so we got to go back to the diagram. Now there's one final thing to note about flip-flops and basically any latched output, so counters too, and is that these cues, you know, when we power up our circuit, we actually don't know exactly just what these cues will be. I mean, they could be high or they could be low. And since we have two outputs here, there's essentially four combinations. I mean, either they're both high or they're both low, or one or the other is high and low. And for our circuit to operate, we need them both low. And we definitely don't want Q1 high, because if we power up our circuit and Q1 is high and then we start the game, it's going to seem as if our player immediately hit the push button, right? And, you know, that's not what we want. So we got to ensure, that at the start of our game, these two guys come out low. You know, say using our reset button that we, the manual reset button that we already made. Now, let's consider the case when essentially Q2 is high and Q1 is either high or low. So those two cases, we'll consider them at once. Because if Q2 is high, well then Q2 naught is low. And if he's low, well then he's going to reset both R1 and R2. You know, it's just going to take, a couple microseconds or so. And so Q2 can never really be high. If he does get high, you know, he's going to die down in a couple microseconds. So we don't have to worry about that situation, as it's already taken care of. So basically, the only situation that remains is when Q1 is high and Q2 comes out low. And in this scenario, you know, that would not be good. And if we remember that in our manual reset button, because we were using the 163 counters with the synchronized reset, like not only when we push our manual reset does it send out a reset signal, but it also sends out a clock signal, you know, a single positive clock pulse quickly right afterwards. And so if we think about it, imagine this one is high, this guy is low, and then we push our reset signal. Well, the clock is attached to the clock input of the second D flip-flop. So when that clock pulse comes, he's going to pull the high into the Q2. So Q2 will go high, and thus Q2 naught will go low, and he'll reset both D flip-flops. And so that's good. So that basically covers the 4 situations. So we don't really have to worry about the Q1 being high when we power up our circuit, as long as we hit that manual reset. Now let's say we didn't use the 163s with the synchronous reset function, but the 161s with the jam loaded ones, because those are quite popular. In fact, I think they're more popular than the 163s. Then we would have to do something about that, because the clock pulse wouldn't be coming. And so we would have to somehow, connect our manual reset to the reset of the first flip-flop. Now, as you can see, it's already being used, because we need to reset it when the Q2 goes low. That's how it works, our little circuit here. And so if we want both options, reset this guy when Q2 goes low, or when I hit the manual reset, then we're going to need, an OR gate, in fact. And so let's think about how that would work. So we want either to reset from a Q2 naught signal, or from our manual reset signal. And so we would need an OR gate. Nice big OR gate like this guy. Now both of these signals are active low. So we could do something like this. We put a little bubble here, and we put a little bubble here. So if this guy is low, or this guy is low, then we want to send a low signal to R1. So if we want to send a low signal, then we put another little bubble right here, and this goes to our R1. And so if we add this gate right up at our R1, then that will do the trick. It'll allow us to reset in 2 ways, the Q2 or our manual reset. Now in the Boolean algebra, using kind of De Morgan's theorem, this OR gate with all the inputs and the outputs inverted, this is equivalent to an AND gate. So in fact, we could just take our Q2 naught and our manual reset and stick them right into an AND gate, and the output goes to our reset 1. And if we implement this in the circuit, we'll for sure use an AND gate instead of an OR gate and 3 NOT gates, because that's what those little bubbles represent. And so we definitely implement it this way. But in our nodes, it kind of makes sense to write it out in this fashion, even though it seems weird with all these bubbles everywhere. And sometimes you'll check like in data sheets and you'll see why the hell they got all these extra bubbles. And it's kind of called assertion level logic. And it sort of makes more sense kind of human-wise, right? Because really, what we want to reset this flip-flop, but in 2 different manners, this way or this way. Anding them, it doesn't really make sense if you spell it out, kind of in human language. It's like, well, no, we don't want to AND 2 signals. We want to reset this way or this way. But of course, the Boolean logic works out equivalently. And so whenever you see kind of circuits with a bunch of little bubbles everywhere, that's the reason. Okay, so this about does it for this pulse circuit here, I hope. And all we have to do is kind of check to make sure that our little finite state machine does in fact work with no bugs. So we have our circuit here with our new and improved push button, and all we got to do is test it out to make sure that little bug is fixed. So power him on, hit the reset, and manually clock it through. Hit the push button this time, and now it should go to the blue. And it does. Good. And now it should not move anymore. No, it stays there. Okay, so it seems like the bug has been fixed. And yeah. Okay, so now that our circuit is working, we can undo this whole operation and build our actual planned LED game, the full-size version. And so what we'll need is essentially 3 of these 2 breadboards here, the lights and the counter with the decoders. And once we have that up and running, we could figure out the serious finite state machine. All right, guys, thanks for watching, and have yourselves a good evening.